What you're watching is a somewhat simple algorithm that can detect pitch from a waveform. Something that's useful for many tasks, such as transcribing melodies automatically, or for algorithmic interpretation of speech with tonal variations. And we will even implement this algorithm in Python in less than 15 minutes. But before we go any further, what do we really mean by detecting pitch? Because pitch is a bit weird. As an example, let's have a listen to these two waveforms. While they look widely different, and definitely also sound distinct, we still perceive the same pitch from them. In this case, the pitch that corresponds to the musical note A. So what's the pattern? How can we instruct the computer to determine this pitch that we humans perceive from these sounds? Let's tackle that problem by starting with an easy example. I'll generate a pure sine wave with an unknown frequency. For a perfectly periodic signal like this one, that is, it perfectly repeats itself, we can find its frequency by determining its period and taking the inverse of that. To find the period, we must find the smallest time shift that leaves the signal looking identical to what we started with. Playing around with it for a bit, we find that shifting the signal by 1/220 seconds, the signal looks unchanged. So that's the period, leaving us with a frequency of 220 Hz for the sine wave, which is the pitch that we perceive. A quick note before we proceed, since you might wonder why we found the frequency and said that was the pitch. Those of you familiar with Fourier series will know that any periodic signal can be expressed as a sum of sine waves at different frequencies, and the component with the lowest frequency is often what the fundamental frequency is defined as, which will correspond to what we found with the method used before if used on more complex periodic signals. But I will also note that pitch perception is an active field of research, and that fundamental frequency and pitch are strictly speaking not the same thing, but they are often used interchangeably, which I will also do throughout this video to avoid spending too much time on the nitty-gritty details. Alright, so our technique worked for the simple sine wave, and we can also find the pitch of many other signals this way, but our method quickly breaks down once we start to modulate the signal slightly, such that it's no longer perfectly periodic. Simply decreasing the amplitude slightly over time will be enough to fool our technique, since we won't be able to find any time shift that leaves the signal looking exactly like what we started with. Inspired by our previous approach, we can try to gradually shift a copy of the signal and then calculate some quantity that tells us how similar the copy is to the original at a given time shift. Continuing onwards, let's stick to discrete quantities. So we will represent our signal as a bunch of samples that have been sampled with a fixed sample rate. We can then shift our copy one sample at a time and then calculate the similarity. One method we could use is to simply take the product of the two signals and then sum the resulting values. In this case, whenever the waves swing the same way, the resulting value contributes positively to the sum, whereas the product will contribute negatively whenever they swing in opposite directions. This function that we've come up with is actually what's called the autocorrelation function, or ACF for short. It's common to define a window around the time step t at which we want to determine the pitch, since sounds from the real world often change significantly over time. So let's add that to the function. Now let's open a text editor and start writing some code so we can see if this technique works. Apart from regular old Python 3, I'll be using the SciPy and NumPy packages. Let's start by defining a function to synthesize a 1 Hz signal that we can test on. Next, let's define the autocorrelation function, which will take the signal, window size, time step, and the number of samples to shift the copy by, which we will denote lag. We will grab a slice of our signal of size W and multiply it element-wise with a copy of the signal, which has been shifted by lag number of samples. We will incorporate the time step parameter by simply shifting all bounds by the value of the time step. Finally, we will take the sum of the resulting data points and return this value. Next up, we will create a function detect pitch that takes a signal as well as the hyperparameters window size, time step, sample rate and bounds, which limit the range of lag values to try. We include the bounds for two reasons primarily. First is that a lag of 0 will naturally give the largest possible value, and the surrounding values are expected to give a similar result, so we need a lower bound on the number of samples to shift the signal by to handle this situation. Second is that while we're limited by the length of the signal, we might not want to try every possible lag value up to this point in the case that the signal is fairly long. These bounds naturally limit the frequency range in which we search for the pitch, so while this can help in reducing unwanted artifacts if we have an idea of what range the pitch lies in, we need to be aware that we risk excluding the actual pitch from the search range. Moving on, we will instantiate a list consisting of the autocorrelation function computed at all lag values within the bounds. Next, we will take the argmax of this list, which finds the index of the maximum value. Since we started calculating ACF values from the lower bound and not 0, we must remember to offset this value by the lower bound, and thus give us the number of samples to shift the signal that results in the greatest autocorrelation value. To convert this to a frequency, we divide the sample rate with the value that we found and then return this. Great, now let's test it out. We will quickly define some arbitrary hyperparameters and generate an array of linearly spaced numbers that will serve as our x values. Finally, let's call the detect pitch function on the signal and print the result. And look at that. As we would expect, it correctly identifies the pitch as 1 Hz. However, we've just tested on a signal that's perfectly periodic within the range that it's defined, so let's instead modify it a bit such that it isn't. We'll do this by decreasing the amplitude exponentially. Alright, moment of truth. Let's see if it works. That's disappointing. It seems that our approach is still ill-suited for the problem we're trying to solve. Let's take a step back and revisit the problem from a slightly different angle, formalizing some previous concepts along the way. For a signal f with period capital T, we have the following equation. Simply put, the signal looks identical to itself after phase shifting it by capital T. From this, we can try to guess the values of capital T where the expression equals 0, like we did earlier. To avoid confusion between the actual period and a guess, I'll use tau for guesses. In practice, it makes sense to make two modifications before we try to implement this in code. The first is to take the sum over a window, which leaves us with an equation that's still true. We do this because unless the signal is perfectly periodic, the equation will never be true. Instead, any deviation will be included in the sum, and our goal is then to look for the value of capital T that results in the sum closest to 0. However, you'll notice that we run into unwanted effects where positive and negative differences cancel out. So to avoid this, we'll square the whole thing. Alright, we have now arrived at a point where we have a new method for estimating pitch. But before we implement it, let's make a quick observation. Look, if we expand this expression, you'll notice that we can easily express this difference function in terms of the autocorrelation function. This is nice because it makes the implementation really straightforward. Let's define a new function df that takes the same parameters as the ACF function. Then we will simply call the ACF function according to the expression that we just derived. Next, we just need to change the argmax call to argmean in the detect pitch function, since we now consider the smallest value our best guess. And there you have it. Our method is ready to be tested. I'll spare you the suspense and tell you upfront that our method still fails the decreasing amplitude example. But before we discard this method completely, we have one more trick up our sleeve. We will normalize the difference function, in a sense, by dividing by the average over shorter lag values, and then define the value at 0 lag as 1. This essentially means that the function will only drop below 1 when the difference function is lower than the average of what we've get so far. So let's quickly add this extra step to our implementation. We'll define a new function, cmndf, shorthand for cumulative mean normalized difference function, that takes the same parameters as usual. We'll use a conditional to handle the case at 0 lag, and otherwise return the difference function divided by the average of df calls with lag values from 0 up to the lag parameter. Alright, let's replace this in our detect pitch function and hope for the best. Finally, our new method managed to handle the case with decreasing amplitude, and it's also capable of handling a multitude of other scenarios that we haven't had the time to look at. If we continue to play around with it for a bit, we'll notice that it still makes a common type of error. Whenever our algorithm makes a wrong prediction, it's often some integer multiple of the actual answer. This happens because a periodic signal is invariant under a phase shift by any integer multiple of its period. So it doesn't matter if we shift it by 2 or 3 times its period, it'll still look exactly the same as the original signal. This is what we see reflected in our method, leading to errors due to the small variations from perfect periodicity. One way we could fix this is to set some small threshold, say 0.1, and then choose the smallest lag value below this threshold. Let's quickly add that to our detect pitch function. We'll add a new parameter, then find the first value below this threshold and save its index. Alright, finally, let's test it out on some real audio. This is what we'll be working with.
Carry me away.
I will add a few more lines of code to load the WAV file into a NumPy array and adjust the hyperparameters. After running the algorithm on linearly spaced time steps, these are the values we get. I'll overlay manually annotated pitches quantized to the nearest tone from the 12-tone equal temperament system so we can get an idea of how it's doing. And look at that. While the transients aren't handled too well, with data points way outside the interval I'm showing, the method generally estimates the pitch accurately and even captures the vibrato in the singer's voice. We can continue to make small incremental improvements, both in terms of making it more accurate as well as improving rigidity and runtime, like padding the signal to avoid crashes or implementing memoization to greatly improve the time it takes to run. But I'll end off by saying that what we've covered here are some of the steps in the YIN pitch detection algorithm from the early 2000s. And in the original paper, a few more improvements are proposed, as well as a nicely detailed description of difficult situations and shortcomings. It's a great paper, so I highly recommend reading it.